All right, well, it's 10:01 and that number's starting to slow down, so I think we'll go ahead and get started. People might continue to trickle in, but they can, they'll kind of trickle in during my introduction, and then they won't miss the good pieces, which are our talks today. So thank you everyone for joining today's webinar on sea level rise and climate change in North Carolina. We have two sets of talks today. First, we'll hear about water level variability along North Carolina's coast. And then following this, we have several related presentations about climate change's influence on coastal on-site wastewater infrastructure. And then we have several additional team members who are on the webinar today who can help answer questions in our Q&A section at the end of the webinar. So just if you've joined any of the other webinars in our series, this is the 5th in a 6-part series covering different aspects of climate change in North Carolina, really focusing on the findings from the North Carolina Climate Science Report and bringing together different researchers across the state who are delving into how climate change is having influences and impacts at the local level. This series is being hosted by the State Climate Office of North Carolina and the North Carolina Institute for Climate Studies. And just a little bit of information about our two centers on the slide here. We're both focused on understanding and researching climate in North Carolina, and we work together collaboratively on some of these challenges. And so we're really excited to have you all here today to learn with us about sea level rise. So just a little bit of quick Zoom etiquette. I know this is probably old hat for a lot of you. Just please keep yourself muted throughout the webinar. Please also turn off your video if you can. Speakers, it's entirely up to you if you want to have your video on or off. I'll turn mine off just as soon as I hand over control of the screen. Once we get to that Q&A portion, everyone please feel free to turn your video back on or leave it off. That is going to be up to you. We will allow questions throughout the webinar. Please feel free to type them into the chat. Usually it's located down at the bottom of your Zoom screen. We'll kind of be collecting them throughout, and then we'll moderate them at the end, or at the end, please feel free to unmute yourself and ask a question too. And then lastly, I am recording this webinar. It will be posted to our website, that URL at the bottom, just as soon as that recording is available. And we'll also upload notes from the Q&A section, as well as some related resources and links. All right, and so with that, we will go jump into our talks. First is Rick Lutich, and Rick, I hope I'm pronouncing your last name correctly. I realize I did not check that, so my apologies if that's wrong. He'll be speaking about water level variability along North Carolina's coast. Rick is a professor of marine sciences and environmental sciences and engineering at the University of North Carolina at Chapel Hill, and is the director of UNC's Institute for Marine Sciences located in Morehead City, North Carolina. He also serves as the director of the UNC Center for Natural Hazards Resilience and has published over 100 scientific papers and reports on modeling and observational studies of the physical processes of coastal systems. So I'm very excited to have him here today to talk with us. So I will stop my screen share, and you are welcome to take it over.
All right, let's see if this works. Are we looking at the presentation?
It is up.
Wonderful. Well, Rebecca, thank you for the invitation to join you all, and thank you all for your interest in this most important topic to the state of North Carolina, particularly the coastal part of the state of North Carolina. Certainly an existential topic, and part of the bigger story about climate change as it impacts the state of North Carolina and the country and the globe. And so I'm pleased to be able to talk a bit about the pieces that I'm more familiar with. As Rebecca mentioned, this is work that has largely been published within the last year as part of the North Carolina Climate Science Report, Chapter 4. And it's work that I did together with Reed Corbett at East Carolina University. And I'm not sure if Reed is on the webinar today, but I definitely want to recognize the fact that this is a joint contribution that I'll be presenting. A lot of the references, not every, there's a little bit more in what I have today than what is in the report, but the real details are there, and the references and all of that are there if you want to follow up. So why does water level matter in coastal North Carolina? And I put the word ocean in front of it because that's largely what I'm thinking of. Clearly, rainfall and other things contribute to water level, and I'll touch on that. It is relevant, but mostly the threat that we are most concerned about is the ocean water level and how that varies. And why does it matter? Well, if you look at large parts of the northeastern coastal area of North Carolina, as well as the central eastern Carteret County and the central portions, but even some of the coastal areas along some of the estuaries in the southeastern part, many of them are within a few feet of current high water levels, and certainly large extents of them are within, say, 5 feet of current high water levels. And so, water tremendously impacts safety, property, livelihoods, and the economies of these areas. And so what the future holds in terms of the water level and what causes it to vary in coastal North Carolina, it directly impacts all of these aspects of life here in coastal North Carolina. And what's more, we of course are ringed by a set of barrier islands from the north all the way to the south. Particularly the northern barrier islands are fragile. They're not too much in most areas above sea level, and thus changes in water level and associated aspects will lead. It's inevitable, really, to degradation of the barrier islands, and with that degradation, there are significant implications. Again, as they degrade, then the sounds inside of them that are largely protected from direct exposure to the coastal ocean and the Atlantic Ocean will become more exposed, and thus the direct threats that poses in terms of hazards along the inner shorelines will change, but also the properties of those inner sounds, the salinities, and simply the exchange with the coastal ocean will change the ecosystems that are there, and so so one can think forward a century or two from now and imagine considerable differences in what coastal North Carolina looks like and how it functions in the broader scheme of things. And much of that isn't well understood at this point, but certainly as time goes on, we'll try to get a better handle on what those changes might really be. So it really is quite an important issue for coastal North Carolina, and thus something that hopefully is worth the webinar today and your all interest. So a few things that go into water level variability along the coast. If you've certainly been to the coast, you know the waves, ocean wind waves and swell are present there most of the time, generated by winds. They're big contributors to shoreline and dune erosion. They certainly cause structural damage when they come into contact with buildings and other structures. And so they're an ever-present part. We don't think of them sometimes when we think about longer-term effects, but they're important. As we look into the future and wonder what waves might look like in the future, certainly they will depend on how the future climate affects the storms in the ocean that generate them. There really haven't been an awful lot of studies that look at how waves might be impacted in the future. The few that have been done, follow along the general notion that storms may be stronger in the future, and thus globally wave power may be more than it is presently. If you look along the eastern seaboard of the US and particularly the coastal North Carolina, it doesn't look like there are particularly strong trends. So I guess maybe the good news is that what we have now may not be bad in terms of future planning. But the big impact of waves depends a little bit on, or depends a lot on where they are in relationship to the land. And so as sea level rises, then the waves that now are breaking on the beach face and perhaps further offshore come closer to the inland, come closer to the dune line, come closer to the structures and the infrastructure that currently is on land. And so even those same waves may have more significant impact as we go forward in the future. And certainly this lower picture is just a reminder of that impact that the waves can bring. This is from the Bolivar Peninsula in Texas following Hurricane Ike. But just an example, most of this area had homes on it. The only one that remaining was substantially elevated. And the bottom line is the waves went underneath it. And all of the other structures and homes that were there were decimated largely by impact from waves. The other very common driver of water level variability, if you spend much time on the coast, is the tides. These, of course, are due to the interactions between the gravitational force of the sun and the moon and the earth. Again, along the North Carolina coast, we recognize and we're familiar with a tide that is typically high twice a day and low twice a day. We call that semi-diurnal, twice daily tide. That's the dominant tide. And it varies along the coast. In the Northeast, it is smaller, say up 3.5 to 4 feet from high tide to low tide. And in the southeastern part of the coast, Cape Fear region and south, it's larger, 5.5 to 6 feet from high tide to low tide on a typical, again, twice daily tidal range. Again, the relationship between these three celestial bodies ends up generating other parts, other aspects to the tidal cycle. Every 14 days, we go through a spring and neap cycle. So every 14 days, the high tides and the low tides are greater. And then in between, they're lesser. And that's the spring neap cycle. Again, more attention of late has been brought to what we informally call king tides, which are the highest tides of the year. And they just, again, recognize the fact that at certain times of the year, we can anticipate the high tides will be more and the low tides will be more than they typically are. And then there are even longer period tides that have return cycles on the order of multiple years and decades. The longest one is 18.6 years. And that, again, just has to do with the relative positioning of the three earthly bodies. But they really, it can influence things, not on the order of feet, but on the order of inches. And I guess one of the themes of water level variability on the coast of North Carolina is it just doesn't take a lot to have an impact. And so inches add up. And so these longer period tidal cycles, depending on where you are, can make a difference. If a hurricane comes when you're at the high part of one of these longer period cycles, then it can be different than if it comes at the low part. As we sort of look into the future, we usually think of the tides as being constant, but the truth is they do change. And what the biggest thing that causes them to change is how man impacts the nearshore areas. And so, for example, dredging can have a significant impact on how the tides behave in coastal areas. And if you look back over the 20th century, back to the late 1800s and early 1900s, some interesting work has found very early tidal records and has shown probably a doubling of the M2 or the semi-diurnal tide up in Wilmington during the course of the 20th century, which is predominantly attributed to dredging in the Cape Fear River. Other water level changes can also affect the propagation and the significance of the tide. So as we get into things like global mean sea level, as that changes, then the tides, particularly again in our coastal areas, will change a bit in response to that as well. So even though we kind of think about the tides as being fairly constant, the truth is in coastal areas, they can change over time. Oops. And another Of course, again, if you're at the coast and particularly live at the coast or have property at the coast, you worry about the impacts of coastal storms and storm surge and storm tide. Storm surge is usually, we talk about storm surge, and it's really wind driven for the most part in our area. And it's the amount of water level change that a wind brings, say, above and beyond what the normal tidal extents are. So that's the storm surge. When you add the storm surge and the tide together, we talk about storm tide. And at the end of the day, that's really what's important, because if a storm hits on a high tide, and say down in the southeast part of the state, a storm surge of 6 feet, if you've got a tidal range of 5.5 feet, well, if it hits at dead low tide, it doesn't look that much different than a high tide. But if it hits at dead high tide, well, then it's a completely different story. So the storm tide is really important. We get storm surge and thus storm tides from both extratropical winter type nor'easters. And we had one last weekend, and I think are due for another one this evening. And those can certainly impact the areas. A recent study done by colleagues at ECU, I believe, have shown an average of about 14.5 of these extratropical storms or nor'easters that have caused storm surge of greater than a foot. And so we deal with those. If you, again, look into the future climate, there's not a really clear pattern of those increasing or decreasing. It doesn't mean it won't happen, but right now we anticipate that in the future, the strength of these storms and the frequencies of these storms may be similar to what it is now. Tropical cyclones are the big ones that we deal with here in coastal North Carolina usually, and of those, hurricanes are the stronger ones. The weaker ones are tropical depressions and tropical storms, and then the stronger ones are hurricanes of the various categories. And coastal North Carolina typically experiences a hurricane about every 2 to 3 years. And our storms of recent record, if you will, are Hurricane Hazel in the late 1950s that had a storm tide of about 18 feet along the open coast, and this was down around Cape Fear and south of Cape Fear. So that's our open coast kind of storm of record. Recently, Hurricane Florence in 2018 had a storm surge. There's really very little tide up in the sounds of North Carolina, the upper sounds, but had a storm surge of about 10 feet in New Bern and caused substantial flooding and damage in that area. And then just last year, Hurricane Dorian was a surprise to many on Ocracoke in that it had a 6 to 7 foot storm surge that flooded large parts of large areas in Ocracoke. The Ocracoke surge, of course, Ocracoke's on the barrier island, and it's endemic of what we oftentimes see on the barrier island, which is flooding from the sound side. And the flooding from storm surge from the ocean side at least has a dune line in many places to deal with, whether it's natural or relic or constructed. And that does provide protection in many cases, depending on how strong the storm is. From the sound side, you don't have dunes along the sound side. And thus, any elevation, any change in water level, any storm surge that's coming from the sounds, really, the only protection you have are the basic elevation of the land. And so with Dorian, this was sound side flooding, and we oftentimes see a lot of the flooding that does occur along the barrier islands as being sound side flooding. We're starting to see trends that show us that hurricanes and tropical storms in particular do appear to be increasing in strength and do appear to have increased in strength over the last 2 to 3 decades. And this is what we predict to continue to occur into the future. And so that's definitely something we need to be prepared for. And the storm surge that occurs from these storms is definitely affected, again, like the tides were, by the basic water depth and water level changes that are otherwise occurring in the system. And we'll kind of come back to that in a minute. But But all of these things do interact and interplay with each other, ultimately to impact what it is we have to deal with here on the coast. I mentioned precipitation at the beginning. It's not what we think about as being our primary hazard, but the truth is that particularly in recent years, we're starting to realize that it is a hazard here on the coast. A lot of the major flooding events that are precipitation have been a bit further inland, say at kind of where the Piedmont coastal plain kind of connect. And that certainly was true for Floyd and Matthew and other storms we've had. But coastal areas are subject to them as well. If you look at this figure on the bottom, one thing you notice, and this is precipitation over the years, most of the large precipitation events were due to tropical storms or hurricanes. So we can get a lot of precipitation from these extratropical events, but hurricanes and tropical storms tend to be the big providers. And it does look as though they're increasing and have increased through the 20th century. Again, there's pretty good evidence from that a warmer climate will be a climate in which precipitation is stronger, and particularly the precipitation associated with tropical storms. And so we expect this pattern, and it does look like we're starting to see it. The good news is a lot of the storms and precipitation that falls inland at least takes a little bit of time, a few days, to make its way to the coast. So we at least can have a bit of separation between storm surge and precipitation flooding at the coast. But Hurricane Florence is the counter example to that. And that was a coastal storm that dropped 30+ inches of rain right in the coastal area. It was a very slow moving storm. And so at that point, we were dealing with precipitation and storm surge on top of each other and concurrently. And we refer to that as compound flooding. And that's certainly an area of growing concern as we begin to appreciate the fact that in addition to the threat from the ocean, the precipitation threat is real and may combine with the ocean threat. Other drivers of water level variability, I just sort of listed a few. Certainly steric effects. Steric means the annual heating and cooling of the ocean. Water expands as it gets warmer, contracts as it gets colder. And so through the course of the year, the water level will change at the coast by, up to about 1/2 foot, just due to this thermal content in the ocean. And so it's highest typically in the early fall to mid-fall when the ocean heat content is greatest. And it's lowest in the winter and early spring when it's less. That cycle exists and we deal with it each year. And then the overall heating of the ocean associated with climate change definitely is contributing to global mean sea level rise. And I'll come back to that in a minute, but that's an important part of just the broader increase, the thermal expansion of the ocean and the global mean sea level rise. The Gulf Stream runs along the coast of North Carolina, and interestingly enough, the strength of the Gulf Stream and the position of the Gulf Stream will affect coastal water levels. And slowing the Gulf Stream actually raises water levels along the coast of North Carolina, and it can affect them by as much as 1 foot. This occurs over cycles of days to weeks. When Hurricane Dorian came through, it actually slowed the Gulf Stream down by about 1/3, which is a little hard for me to believe given the momentum and enormity of the transport and the flux of the Gulf Stream. It was slowed by about 1/3 by the winds and the forces that Hurricane Dorian imposed on it. So it's there, and also its location tends to cycle through a couple of different kind of standard positions, if you will, over a 2 to 5 year cycle, and that will also affect water levels along the coast. The Gulf Stream is part of a bigger circulation process that's called the Atlantic Meridional Overturning Circulation. We have pretty good evidence that has been weakening through the 20th century, and that's consistent with future predictions that future climate states will continue to weaken it. Again, the Gulf Stream is part of that, so we might anticipate that in the future we'll be dealing with a generally weaker Gulf Stream, which again may have implications on long-term water levels and sea level rise along the North Carolina coast. And then there are a number of other processes that we may be familiar with some of the names: El Nino, the Atlantic multi-decadal oscillation and whatnot, combined ocean and atmospheric processes that have cycles that range from a year to decadal in nature. Individually, their responses on water level may be small, again in the inches category, but again, cumulatively, they can become significant. A lot of work is being done to try to better understand how future climate is likely to impact these, but I think that research remains fairly nascent. And the point is that these are all processes that together contribute to the variability of water level along the North Carolina coast. So at this point, I'd like to now kind of get to the meat of what we think of when we think of climate impacts on water level, coastal water levels. We usually refer to them in the context of relative sea level change, relative sea level rise typically. This has two components. One is how the land elevation itself changes, and then the other is how the ocean elevation changes. If you're on land and the water level itself is staying completely still, but the land is sinking, then you certainly have the perception that the water level is rising just due to the fact that you're sinking. Along coastal North Carolina, interestingly enough, if you look in the southeast, and these are the reason for these are the various geological processes and provinces that exist in coastal North Carolina. But in the southeast area, this region 1, we're actually, the land level is actually rising slightly, an average of about an inch per century or 0.01 inches per year. In the northeast, on the other hand, the land is sinking and sinking about 4 inches per century or about 0.04 inches per year. And in the middle areas, say the Carteret County areas and in the middle parts of the state, we don't have as much good data, but the expectation is that it's sort of in between these two values, and so it's probably sinking slightly over the course of time. So this is what we see happening as it relates to land elevation change. And it's good to kind of keep these numbers 0.01, a hundredth of an inch per year in mind as we then switch and look at what ocean elevation changes kind of look like over time. And so we kind of refer to this or think about this as global mean sea level, how the global ocean is changing. For 2,400 years, or 2.5 centuries or so, it was relatively constant, plus or minus about 3.5 inches. Up until about the beginning of the 20th century. And then it's gone on a fairly sustained and fairly rapid rise to the present date. Not only has it risen, but the rate in which it's risen has been increasing. And so if you look at the rate of rise over the first 9 decades of the 20th century, it was about 0.06 inches per year. So not terribly different from that land elevation change, at least in the same ballpark, but it's risen again that much. If you look at the first or a decade and a half, a decade early in the 21st century, then it's been more than double that rate that it's risen. Almost 2.5 times that, about 0.14 inches per year. And the reason for global mean sea level rise is predominantly twofold. I mentioned earlier the Steric Effects, just the warming of the ocean, and that certainly contributes to the global mean sea level rise. Although what we see is that the melting of the ice sheets and land-based glaciers actually contributes about twice as much to global mean sea level rise as Steric Effects does today. And really, starting about the beginning of the 21st century. They were comparable in size, but the acceleration in the melt of land-based fresh water really has really started to dominate rises in global mean sea level. And that's what has led to the acceleration of global mean sea level increases. As we look into the future and try to anticipate what climate change over the course of between now and say 2100 is likely to produce, it really boils down to how what the greenhouse gas rates or how the anthropogenic impacts on climate change, what they look like. If we look at the IPCC scenario in which we stop putting a greenhouse gas into the atmosphere, or we peak our greenhouse gas emissions this year, and then it declines to zero, and particularly carbon dioxide emissions decline to zero by 2100. That's what they call RCP 2.6. In that scenario, we still end up with a sea level rise rate that's faster than it is today, and maybe as much as double, 0.16 to 0.35 inches per year. And following that through by the end of the century, the 21st century, we're looking at sea levels that are 1 foot to 2 feet above, say, their value in 2000. So now not just inches, but rather feet. And that's the sort of the best case scenario where we really control things now and through the rest of the 21st century. The worst case scenario is typically considered to be this RCP 8.5, which is sort of the business as usual. We continue with our current rate of or current projections of greenhouse gas emissions. And in that case, the sea level rise almost certainly doubles to maybe quadruples in inches per year. And the result at 2100 is a water level that is a global mean sea level is 2 to almost 4 feet higher than it is at the beginning of the 21st century. So substantial impacts, substantial implications for coastal North Carolina in this regard. So let's try to put the pieces together and what does this kind of mean for coastal North Carolina? I look at it at 2 different levels. One is just the high tide or sunny day flooding. In the absence of any storm, occasionally today on king tides or other things, we'll get situations where these pictures are from the town of Beaufort, Carteret County, central North Carolina. We'll get situations where Front Street in Beaufort is flooded, and that happens, say, a few times, 2 or 3 times a year today. But if we imagine a sea level rise, which is somewhere between the business as usual 8.5 or maybe a more modest intermediate level, which is the 4.5 level, which basically says carbon dioxide emissions continue through about the mid 2040s and then decline after that. But if we look at that range and then look at what the implications are on just this high tide flooding, whereas again, early in the 2000s, just a handful of times a year doesn't really show up on this plot. By the time we get to 2050, we're in the range that it may be as often as 100 days a year, 1 to 2 days a week even. And that's probably in my lifetime that we could see this. As we get to the outer parts of the 21st century, then we're into a situation where it could be happening every day. In almost all likelihood, it will be happening multiple times a week, but maybe daily. And so this is for Beaufort, but there are many other coastal towns along the coast of North Carolina that are in a similar situation and really need to start thinking about what the implications of this are for their long-term existence. And North Carolina, of course, isn't the only area that's dealing with this. The Hampton Roads, Norfolk, Portsmouth area of Virginia, this is a big issue today. Even Charleston is seeing a lot of this, and certainly other areas, but North Carolina is seeing a little bit of it, but can certainly expect to see much more of it in the future. So this is just sort of in the absence of storms, but what happens when some of these hurricanes come along that we have today? What can we expect to see? And this is an interesting recent study that kind of compares the flood levels, the water levels from hurricanes that we see today versus what we could expect to see towards the end of the 21st century. And today, and this is central North Carolina, the example, if there's an annual 1% chance that the water level might hit about a meter or so, a meter, 3 to 4 feet in height today from these storms, then in the future, what we're looking at is more like 2.5 to 3 meters. So instead of 3 to 4 feet, we're talking 6 to 8 feet. So major differences in what this 1% event is likely to be along our coast. Also, again, if the 1% flood today is this level, if you look back at what that same degree of flooding is likely to be in the future, what we're likely to see is that it has more like a 30% chance of happening every year in the future. So basically, every time a hurricane comes through in the future, we're likely to see what today we anticipate as being something like a 1% or a 1 in 100 year event, maybe happening 30% of the time or every couple, 2 to 3 years in the future. And so this is obviously quite concerning for the future. I mentioned that there really are two things that contribute to this high level. One is the sea level change, and the second is the change in the tropical cyclones themselves, the strengthening of the storms. What this study showed very clearly is that in North Carolina, at least, the difference between the black and the blue lines is what's due to the strengthening of the storms. And that really is small compared to the difference between the blue and the red lines, which is what's due to the sea level, global mean sea level change. And so really, the real issue that we're going to have to deal with in coastal North Carolina, whether it's sunny day flooding or the impacts of severe storms, is changes in global mean sea level. So just to kind of conclude, a few takeaway points, if you will. It really doesn't take a large change in water level to impact significant portions of coastal North Carolina. And I would say inches matter and feet can be catastrophic. There's many drivers of water level variability and relative sea level rise. But when you add them all together, then there's certainly significant high tide sunny day flooding that will be occurring in many parts of North Carolina in the second half of the 21st century. We already see indications of it today, but it's going to become much more prevalent, much more something that has to be dealt with, and will require a change in the way we do things on the coast in the latter half of the century. North Carolina is highly vulnerable to major storm surge from hurricanes. It's climate change causes global mean sea level rise and the strengthening of tropical cyclones. But really, the global mean sea level rise is probably 2 to 3 times as more significant in terms of the impacts of what hurricanes are likely to do along the coast of North Carolina in the latter part of the 21st century, as compared to the strengthening of the storms. Now, that doesn't mean one big storm might not hit us. It could hit us next year, could hit us in the latter part of the century, but statistically speaking, it's the sea level rise that really is what's the greatest threat. And as I just talked through, something that has a 1% chance or a 1 in 100 year storm this year may have a 30% chance towards the end of the century, or once every 2 or 3 year kind of average return period in that time frame. And then lastly, the issue of precipitation. All of this is the ocean response and impacts on the coast, but certainly precipitation is a growing concern, and particularly when it is superimposed on the storm surge from the ocean. So with that, I'll turn the controls, I think, back over to Rebecca.
Thank you, Rick. That was incredibly informative. I feel like I need to take a moment to take it in and come to terms with it for in some ways. But I really appreciate how you broke down the different components and factors that go into sea level rise and what that means on our coast, from the very local level to the global level, in connections with patterns. We've had a couple of questions come in through the chat, so I look forward to kind of delving deeper in the latter part of the webinar. So thank you very much. Up next, we have kind of a sort of joint presentation on climate change influence on coastal on-site wastewater infrastructure. So first we'll hear from Dr. Michael O'Driscoll. Dr. O'Driscoll, is a U.S. Navy veteran and has been a faculty member at East Carolina University since 2004. And his research focuses on utilizing tracers and other hydrogeological, geochemical, and geophysical techniques to develop insights into the geological controls and land use effects on contaminant transport, particularly in the nutrient-sensitive coastal plain and Piedmont watersheds. And then we'll hear from Dr. Jane Harrison, the North Carolina Sea Grant Coastal Economics Specialist. She applies economic analysis and other social science methods to meet the needs of coastal residents and stakeholders. Her work informs coastal decision makers about the intersections between sustainable use of ocean and coastal resources and economic development. And then last but not least will be Katie Hill, a research professional with the University of Georgia Institute of Government. Helps governmental clients develop solutions to environmental policy and planning challenges. She's an attorney who's been with UGA since 2008 and the Institute of Government since 2020. Katie's work currently focuses on climate change, adaptation, wastewater management policies, and oyster aquaculture. And I took a sneak peek at their slides before, so I'm really excited to see their presentation. So with that, I'm going to stop sharing, and Mike, please feel free to take control.
Yeah, good morning, everybody. Can you see my screen okay?
Looks great.
Okay, great. Well, thanks so much. And thanks, Rick, for a great presentation. A lot of what Rick just talked about will really set us up for this presentation. And since it's getting close to the weekend, I thought this is a great opportunity for us to virtually take a trip to the beach. So we're going to hop over to the coast and look at some of the climate change influence on coastal on-site wastewater infrastructure. So you may have seen images like this one, looking at the Outer Banks and some of the storm effects, and this can be very abrupt, where coastal erosion can cause septic systems to be unearthed, and it's pretty evident then from this image that those systems aren't going to function after that sort of extreme event. But we'll also talk today about some of the more subtle changes, as Dr. Lutich talked about sea level rise and how it can affect water levels. There are subtle changes with the groundwater that can also impair these systems. And what people have started to see in the research is that these groundwater levels near our coast are rising, as Rick spoke of, extreme precipitation events too increasing. And you may have heard that over the last few years, this has really come to a head in Miami-Dade County, Florida. Here's just a headline from CNN last year where they're saying this is one example of climate change where you may actually be able to smell it, right? Basically, septic systems getting flooded out by rising groundwater levels. And what's happening in Florida, it's been observed in Rhode Island, and also we could say it's happening here in North Carolina. Here's just an example from last month, Tropical Storm Eta, when it came through in Nags Head, one of the systems we were looking at, it got flooded out. And so these changes along our coast can pose a threat to our on-site wastewater treatment systems, and those can have an impact on public health and also the water quality in our coastal ecosystems. So the question is, how can coastal communities that use on-site wastewater treatment be able to protect their water quality as the climate changes and these systems may not function as they did decades ago? So This is the project we'll talk a little bit about today. And so Jane Harrison is leading this up at Sea Grant with help from Lauren Voorhees. And Jane will talk next. I'll pass it over to her. We have an interdisciplinary group. Eric Edwards is an economist, Jared Bowden, a climatologist, and at ECU myself, Charlie Humphrey and Guy Iverson have been working on the hydrology and the onsite systems. And then Katie is a legal expert, and she'll kind of finish up the talk. And we've partnered up with Nags Head, North Carolina, and Folly Beach for this project. So the idea is that the changing conditions in our coastal regions can cause unique wastewater management challenges. Some of the aspects that Rick just talked about, like sunny day flooding, nuisance flooding, higher tides, extreme precipitation events, and sea level rise can all threaten these systems. So this is kind of a broad question for our coastal communities. How can they effectively and legally implement climate adaptation plans for their decentralized wastewater infrastructure? So it's a big challenge up and down our coast. And today we're just going to talk about some of the preliminary results from some of this work from some interdisciplinary perspectives. So I'll talk a little bit to start with on the groundwater dynamics. And then Jane is going to talk about expert interviews with on-site system operators and installers and health officials. And then Katie will finish up with some of the legal analysis. So when we look at North Carolina, we are very heavily reliant on on-site wastewater treatment systems or septic systems. We have about 2 million systems in the state, and about 1 million of these systems are in watersheds that drain to our coast. When you look nationally, we have the 4th highest number of systems in the country, or at least percent of population using these systems. And within the Southeast, we have the highest percentage of people, about 49% of residents use on-site systems. So it's a pretty broad approach for treating wastewater, and it can work well in the right conditions with deep water tables. So what's kind of transitioned with a lot of our rural communities near the coast is up until about the 1970s, every coastal community that was pretty rural was very heavily reliant on just traditional conventional septic systems. And since the 70s, technologies have been developed for more packaged treatment plants that have advanced technologies and advanced pretreatment systems. So there's more technology and engineered systems to help with this waste. But you can see in the figure on the right, most of our wastewater treatment systems are these decentralized systems that treat waste at the site. So packaged and advanced systems and then traditional conventional septic systems make up most of the systems in our coastal counties. So when we look at conventional systems, this is just an example at a residence how the waste would be treated. It would go to the septic system and then drain out to the drain field. And the drain field relies on having unsaturated soils beneath it. And in these unsaturated soils, that's where most of the treatment occurs. So the difference there, the distance between the drain field and then the water table, that's called the vertical separation distance. And this is very important for on-site wastewater treatment because the deeper you have to the water table, the more unsaturated soils are present to help retain and treat some of the nutrients and bacteria. It also allows for aerated conditions that can help to convert some of the nitrogen to nitrate. What the field and column studies suggest is that for adequate soil treatment of on-site waste, we need about 60 centimeters or more of vertical separation distance. And so when we think about coastal areas, you can imagine near the coast, the water table is a lot closer to the land surface, and this image shows that. So it's a lot harder to find areas where you have a very deep water table that would provide adequate treatment of the waste. So when we think about climate change threats to our on-site wastewater treatment systems, there's the example I showed before where you can have really acute changes with storm-related erosion where you can wipe out a system very quickly. But there's also the more subtle effects of flooding. And so this is an example here after Hurricane Florence for Pitt County system. And basically, the large amount of rainfall that occurred during this event caused the groundwater table to rise up into the drain field trench. And so that for some duration, it can be days to weeks, there's no treatment occurring. There's no unsaturated soils underneath that system. And so it can take a while for the groundwater to recede and get back to levels where that system would be functioning properly. And then the other more subtle effect is when we think about groundwater levels underneath these systems. So a properly functioning system will have a good vertical separation distance, and that waste will percolate down through the soils and get some treatment. But in areas where we have rising sea level, the groundwater level can rise up and sometimes can rise up to the point where it's in the drain field. And so this reduces the vertical separation distance. In North Carolina, the regulations suggest we need to have 30 to 45 centimeters of vertical separation distance to get treatment of the waste. And these kind of chronic failures can occur as the water table slowly rises. It can reduce that vertical separation distance. So just going back to some of the work they've been doing in Miami-Dade County, where they have a large number of systems that are compromised, and they started to class their systems based on systems that are functioning, where they have a thick vertical separation distance. And then some of the changes that have occurred as the groundwater table has risen over time. So you get compromised systems that can't exist, where the water table then has risen up to a level where you don't get the same unsaturated zone beneath your system. And so you lose some of that treatment capability. And then the worst case scenario is to the left, where you have failed systems, where the water table has risen enough that the systems are chronically submerged. And so there won't really be good treatment of that waste. So I'm gonna shift gears now and just talk about some of the groundwater level data in Dare County, where we've been focusing for part of this project. And so first, I'll show you the groundwater wells that the North Carolina Department of Environmental Quality has, and those are in orange here on this figure. And it's a really great database. They've been collecting groundwater levels there since the 1980s. They've had about monthly data collection. And then in 2003, they started to put loggers in these systems. So they actually have daily data at most sites by 2008. Up at the top of the figure here is the duct tidal gauge. So we have good sea level data pretty close to these sites, and we can compare the groundwater levels to that. And then in green, we have some water quality wells as part of this project, where we can also monitor water quality. So for this section of the talk, I'm just gonna focus on the longer term DEQ groundwater data. So this figure here shows the mean annual groundwater levels in these 8 DEQ groundwater wells, and also the sea level rise at duct for mean annual conditions. And so basically you can see that these groundwater levels are typically rising in almost all of the wells that they're monitoring. And then the sea level rise at duct that has a very good record there, they estimate about 5 centimeters per decade of sea level rise. So when we look at the groundwater level trends at these sites, the mean annual groundwater levels were rising significantly for 7 out of the 8 sites. The only exception is the Stumpy Point site further inland down there. Median groundwater level rise trends for these sites was about 13 centimeters per decade, so about 5 inches per decade. And it ranged from 29 centimeters per decade to 6 centimeters per decade at the sites. Those are both on Roanoke Island, Wanchese site, and the Skyco Road site. And I'll talk a little bit more about the Wanchese site that had the highest rate of groundwater level rise. So when we parse out the data and separate it out by the decades that they had groundwater levels at this site, you can see here that there's a groundwater level rise at this particular location of about 0.63 meters since the 1980s, if you look at the median change for those decades. So this was a site with the greatest groundwater level rise out of all the 8 wells. And you can see when we went out after Tropical Storm Eta, you can see there's some ponding at the site there. So when we look at this from a groundwater depth perspective, over time, what's been happening is the groundwater depth has been shrinking at these sites. And if you consider what's needed for functional on-site systems, basically the drain lines are typically buried about a ½ meter, and the vertical separation distance required by the state for these sandy soils is about a ½ meter also. So 1 meter is kind of a good range to look at. If you have groundwater that's deeper than that, it would be suitable, and groundwater depth that's shallower than that would be generally unsuitable. And what we could see is that based on these groundwater depth data, that the vertical separation distance has been declining over time. So systems in this area that would have worked back in the 80s and 90s currently wouldn't be functional. So looking broader at all the data then for groundwater depth, the majority of sites where they have wells showed groundwater depths that were typically less than a meter. So these areas wouldn't be viable for conventional on-site systems. Only 2 areas had groundwater depth that was greater than a meter for 30% of the year. Both are on Roanoke Island, the Skyco Road site, and then the Manio Airport site. So looking at storm response then, so that's sort of looking at longer term groundwater level rise, but also one important factor is how the groundwater level changes after some of these large storm events. And so this is an example from the Wanchi site of 18 centimeter or 7-inch extreme rain event. And what happened during that event in October 2012 is the groundwater level rose about 1.2 meters or almost 4 feet. And so when we look at how long it would take for that groundwater level to get back down to the pre-event levels or to a level where systems could function, it could take something like 100 days for that groundwater to recede. And so when we look at this site over time for some of the large rain events, anything over 2 inches or 5 centimeters, we could see that in general, it takes weeks to months for the groundwater levels to return to pre-storm levels. So that would indicate that systems would not be functional for some period of time after these storms. And so looking at the bigger question of why the groundwater levels are rising, and these data are for the superficial aquifer in Dare County, there's a strong correlation with sea level rise. So that explains part of it. As sea level is rising, the groundwater levels in the superficial aquifer are also rising. And then during years when we have elevated precipitation, this can also cause the groundwater to be higher than normal for some period of time. So the mean annual levels will also show a rise. The other issue in this area appears to be that the water supply is coming from the deeper Yorktown aquifer system. So it's separated by a confining unit. And this groundwater is pumped from depths 100 feet or so. When we look at the mean groundwater levels in the Yorktown aquifer system in that region, they're actually declining. So they're showing an opposite trend compared to the superficial aquifer levels. And in a lot of other areas, they've pointed this out that when you change the pore pressure in the sediments, it can cause more subsidence to occur. So that may be a possibility. And Rick also talked about how there's natural subsidence occurring in this area. And the other factor appears to be that when you take the groundwater from the deeper aquifer system and then we use it, that water gets recycled back into the superficial aquifer through the on-site wastewater treatment system. So people use it in their house and then it's discharged to the superficial aquifer. So it's a source of artificial recharge to the superficial aquifer. So this may also influence the groundwater levels. And then there's also other potential factors such as deforestation, where as you remove vegetation, it can change the evapotranspiration, and trees will pump groundwater and can cause lower levels. But if you remove them, that will change some of that pumping effect. Other issues could also be related to drainage and stormwater associated with impervious areas. So The question we're looking at is in how are these rising groundwater levels affecting on-site wastewater treatment? And so we started to look at some of the water quality aspects, and we'll talk a little bit about that later. But next up, I think it's real important to then ask the experts that are working on these systems. And lucky for me, Jane's been doing that. And so what I'm going to do is stop and share it over to Jane. So I'll release my screen sharing. And now it should be open for Jane to take that over. Thanks, Jane.
All right, great. Thanks, Mike. Can you see that all right?
Yes.
Okay, very good. Yeah, hi, good morning all. So I am gonna pivot here and talk a little bit about some of the folks that work day in and day out with these on-site wastewater treatment systems. So I've been working with Lauren Voorhees at North Carolina Sea Grant to put together surveys and interviews with our, on-site wastewater treatment system operators and installers, as well as health officials that are charged with permitting and regulating these systems. I'm just going to speak for a few minutes today about some of the results from this work, and specifically what we're hearing from the on-site wastewater operators. So this is just an example photo. They're pumping out a septic system in South Carolina. Let's just look at who we've been talking to. So overall, we're actually focused in this work in the coastal Carolinas. So we're looking at the Atlantic coastal plain in both North and South Carolina. And so our study area in terms of determining who we interview was any wastewater operators or health officials in this region. So you can see so far who we've surveyed and interviewed, and Lauren has been doing this work to make these connections with folks who work in these fields. So you'll see we have a good mix from both states, and we're still working to do a few more surveys and interviews with the health officials. But right now we have 20 wastewater operators, and I'm going to report on just a couple of findings, kind of their perspectives on these topics. How does extreme weather influence these systems, and what are they doing as our climate changes? Okay, so in terms of who we're talking to, most of these folks, they work in a mix of the outer coastal plain, as well as a few in the intercoastal plain and the sandhills. The majority, over half, do work on barrier islands or sea islands, and most have more than a decade or even 20 plus years of experience doing, on-site wastewater treatment system installation and operation. So in terms of, the site conditions that really affect the functionality of these systems, obviously it does go beyond weather and climate. And so we asked them to tell us, what are they looking at in terms of thinking about functionality during some of these extreme weather events. And so, most important certainly is drainage, the rate at which a site can dispose of the water or drain the water away from the system, and then allow that dispersal field to dry out. Specific aspects of drainage, they're related to the soil type, the soil percolation rate, soil absorption, soil texture, elevation, groundwater height, slope. These are all very important. And so we asked them, what were some of these conditions that determine function in both heavy rainfall as well as frequent rainfall events. So they were very similar in terms of, the site conditions that impact. Now, another question that we were asking them was to consider 3 hypothetical weather scenarios and how they would expect a conventional septic system to handle the conditions. So I'm just going to briefly go over those 3 scenarios. The first one was dry conditions and heavy rain. So we asked them to consider dry conditions that are going on long enough to create very dry soils, and then after which there's an intense rainfall event, so let's say 2 inches of rain in one day, and with that kind of an event, only 2 of those interviewed said this would cause malfunction. So that was not so much of a concern if you have the dry conditions and then a heavy rain event. But let's look at another scenario where we actually have some wet soils and then a heavy rain event. So the second scenario, we asked them to consider an inland coastal area. So an area that's at least a mile from the ocean, and the soils are saturated from prior rainfall. And then there's that heavy rain and fall event. So we've got that 2 inches of rain in a day. Now, in this case, more than half said the system was going to malfunction. And so when we asked them how long it would take to recover, there were a lot of different responses, and they really went back to those site conditions. So what exactly is going on in that site day to day? What's the perk rate? What's the elevation? Things like that. But they said, anywhere from say 2 days to maybe a month. So one example was after Hurricane Matthew, that it would have taken at least a month for these systems to come back on. As you just heard from Mike, from some of his data and research, really it could be 3 months. So this is kind of the perspectives from the wastewater operators. It doesn't mean that they're going out to evaluate or monitor these systems after each one of these events. This is just, kind of what their take on it is. Now, the third scenario is wet soils and then a king tide event. So we asked them to consider a coastal area within 1 mile from the ocean. And so again, those soils, they're saturated from prior rainfall, and then the area experiences a high tide or king tide event that causes a high tide that is 12 inches above average. And in this case, we had even more that would consider that to be a scenario for a malfunction of your system. And again, maybe upwards of 30 days, depending on your site conditions. So it was a kind of variety of responses. Some folks said, okay, it'll take maybe 2 to 7 days or 2 weeks or even upwards of a month to come back online. And so really, when these systems are malfunctioning, what can you do? Ideally, you're letting the system rest. You're not using it, but generally folks are still using their systems if they're, still in their homes. Now, finally, I do want to mention some of the adaptation measures that the wastewater operators are starting to take on. So when we ask them, are you taking any adaptation measures to deal with extreme weather events currently? Over half said yes. And so these are just some of the things that they are doing. They are raising septic tanks up with fill to either be partially or completely above ground. They're raising the drain field to be shallower or above ground. They're really trying to create that greater vertical distance to the groundwater table. A number of them said they are coming up with more conservative installation measurements and recommendations for depth and loading rate of systems. So you can imagine, if they were going to install, let's say, 1,000-gallon tank or maybe a 1,500-gallon tank, instead they're going to, maybe double that or go up to 2,000, maybe 2 1,000-gallon tanks, a greater capacity for these systems to handle what's going through them. And they also mention a number of advanced systems that they find do better in some of these events. So whether that's pre-treatment, drip irrigation, chambered systems, pressure systems, curtain drains, there's a lot of options out there. That being said, they all have a cost, so it doesn't mean everyone is using them, and they're actually quite uncommon at this point, according to those we've interviewed. I am going to turn it over now to Katie Hill, who's going to speak a little bit about some of the policy options when it comes to on-site wastewater systems.
Hey, everybody. Thank you for having me. My name is Katie Hill, and I'm happy to be here with y'all today. Jane, thank you for switching the slides for me. There are only 2 of them, so it's not a tough job. As Rebecca said, I'm a lawyer and I love septic systems. So I have got a lot of information about septic system policies over the years, and this is a fun thing to talk about. So Jane just alluded to a few of the things that that might be possible adaptation policies or options for septic systems and other on-site systems that are impacted by sea level rise. Because, you know, we get all this information about what is going to or what might happen. So I'm here to tell you what we might be able to do about it. First, I'll talk about some of the policy options, and then I'm going to talk to you about some issues we have with the way that we're going to be able to implement some of these options. Okay, so the first thing that I'll tell you about is land use planning and zoning, a traditional function of local governments. And we're going to need to do some land use planning and zoning changes in order to accommodate rising seas. For future development, it's going to be incumbent on these coastal communities that are vulnerable to identify areas where in the near or distant future, it's probably not going to be a great place to have on-site wastewater systems. They should be doing this for other types of infrastructure and for other impacts as well. And certainly on-site wastewater should be included in that type of land use planning option. Land use planning and zoning, however, is a great tool when we're talking about that future development. But when we're talking about the systems that are already in the ground, these existing systems, it's quite possible that this could be a much more limited tool. And I'll talk a little bit more about that on the next slide. The next type of potential policy option that could be utilized would be stricter siting and installation rules. I should have design on here as well. So Jane just mentioned some of these installers are pushing for, say, bigger tank sizes or curtain drains or these types of design changes. That would be another rule change or management change that could fall under this category. Again, this is going to be necessary for future development, particularly that vertical separation distance between the drain field and the water table. Some places it's a lot shallower than we would typically recommend. So that needs to be, those distances probably need to be a bit deeper. Though, just like with land use planning and zoning, this is going to be necessary for future development. But again, the focus is going to be on new systems, either brand new systems for new development or for systems that have had some problem with them such that they will need a completely new system on the property or major repairs. Typically, with on-site wastewater rules, existing systems, when there is a rule change, are going to be grandfathered into the permitting scheme. There could be a decision going forward not to grandfather in those types of systems, but I don't recall ever seeing that done yet. So again, these stricter siting and installation rules for the time being are probably going to be more in line with looking at new systems or replacement systems. Maintenance requirements for on-site systems. This is something that's been pushed in many parts of the country for many years, because in most places we actually aren't requiring people to maintain their conventional septic systems, your regular run-of-the-mill gravity-fed septic system. In most places in the country, you don't have to get it maintained according to some local ordinance or state law. And maintenance can, and when we talk about maintenance, what we're talking about, the most common type of maintenance is pumping the solids out of the septic tank itself. That usually has to be done between, I think, every 5 to 7 years, depending on the size of the tank, how many bedrooms in the house, and some other factors. But when it's done regularly, it can extend the working life of the system, and it can also, in cases where there's a high water table and saturated soils, and the soils can't accept too much of the effluent from the septic tank. If you've got a well-maintained system, you might have more leeway in terms of the time you have available to let those soils become unsaturated again and start accepting the effluent from the system. Maintenance requirements are great. We should have them, but they're not going to be a long-term remedy for sea level rise. I mean, you can't just pump out your tank, every day, and that's not going to be something that's going to be the nail in the coffin for our adaptation measures. Another thing that Jane alluded to is advanced or alternative systems. So we have a number of different types of these systems that have been used for quite some time. And they will definitely be an option for some, maybe a lot of sites. One common example would be a mound system. We've talked about the issue with that vertical separation distance, right? You need that to be able for the wastewater to be properly treated, and so that it'll actually get out of the tank and percolate down. You've got problems on both ends, backups into the home and the quality of the effluent getting down into groundwater. The mound system, basically what you're doing is creating a new drain field with dirt you've brought in on top of the ground. So you get a mound and you pump the wastewater from the tank up into the top of the mound drain field, and it percolates down there. So you're creating an artificial vertical separation distance with all this dirt you brought in. Those have been used, I think, rather successfully in a lot of places across the country. And that would be one of a number of different options for these advanced or alternative on-site systems. But as Jane alluded to, these systems are not inexpensive. I say a figure I hear a lot is usually between $10,000 and $15,000 for a system like this. And if you have a difficult site, which many of these coastal communities, these coastal sites might be kind of problematic in terms of what they've got going on there, that could drive up the cost. And also these systems do require enhanced management. So I think maybe a good rule of thumb would be that, at least every 6 months, you're going to need somebody to go out there and take a look at the system, make sure it's working properly, because they do usually include electrical or mechanical components that you need to keep an eye on. Another option is something that's called a cluster or a community wastewater system. I like these systems because they're a flexible alternative, and they also give you an option of kind of creating a wastewater utility for these homes that thus far have been, on wholly privately owned decentralized wastewater systems. So a simple way of thinking of a cluster community system is that it's like a big drain field. That's a little too basic, but it's a good way to think about it. One type of system you might have is that everybody keeps their septic tank in their yard, and then there's a community drain field, perhaps with some other type of advanced treatment added on to it somewhere nearby. Like I said, these can be great options. It's a way to kind of take care of a whole area at once. You can have centralized oversight, hopefully from the local government or some other responsible entity, making sure the system is working properly. There are other advantages to them as well, but they do need, the suitable site. You need a place that's going to work to take the wastewater if you're doing disposal into the ground. They can be expensive, and I think local government management or some sort of local government involvement is definitely, if not necessary, incredibly appropriate for these systems. And if the local government isn't interested in being involved, it might be a little tricky. How are we looking on time? Oh goodness, I'll be fast. All right, so centralized sewer is something that we hear a lot. You get advanced treatment, centralized management. But it's really, really stupid expensive, isn't it? And there can be permitting issues as well. If you have nowhere you can get permitted to discharge the wastewater, how are you going to make it happen? And local government liabilities as well. Now you're talking about taking local responsibility for supplying adequate sewage treatment when before it was a private system. And if things start going bad with the centralized sewer system because of sea level rise, now the local government might be on the hook there. And then finally, retreat is always just an option we have to think about in these communities. And some places are actually developing policies that are requiring managed retreat, such as Norfolk, Virginia. But of course, the cost, the political will, and potential legal liabilities as well for retreat programs can be tricky, to say the least. Okay, Jane, we'll go to the next slide now. And I'm going to talk to you guys about, so here are all these options that we have, right? All these great things we could be doing. But if we're going to do those things, who's it going to be? Who's going to do it? In coastal communities, the two entities that are the likely targets for this type of on-site wastewater adaptation policy implementation would be local health agencies, your health departments, those types of entities, and then the local governments. But what we find here is something that's really very common with sea level rise adaptation policies. What we find is that we have some regulatory barriers here. And what a regulatory barrier is a policy or the way that policies work that make it either impossible or particularly difficult to implement a particular policy option. And they're very common with sea level rise adaptation, other types of climate adaptation and climate policies, because we're operating under a lot of policies, laws, rules that were adopted back when we didn't really appreciate the significance of the impacts of climate change. So the things that would help us adapt to climate change and otherwise confront it just have not been worked into these policies, and they haven't been included over the years. And so the major issue that we have, I think the most pressing first line issue that we have for on-site wastewater adaptation is this question of legal authority. And I'll quickly go over kind of what the issue is here. So the local health agencies, those are the entities that on a day-to-day basis, your local health department, they're the ones who are out there dealing with directly permitting the day-to-day management installation of septic systems. You got a problem with your septic system, you need a new permit, you call the health department. But the rules that they operate under were by no means developed to consider changing conditions, particularly from sea level rise or climate change. And they also, the rules focus on imminent public health hazards. So if there's poop on the surface of the ground because of your septic system, they're concerned about that. If there's no septic system and there's a straight pipe discharging poop into the water, they're concerned about that. If there's a little bit of nitrogen or phosphorus that's getting out of the bottom of your system because sea levels are slowly rising, it's getting a little bit worse over time, they're not going to make you change your system because of that. And it's not, not their fault. These are the ways the rules were developed. Also, installation of these systems and permitting, which is often like kind of the only time they really go out there and take a look. It's based on snapshot in time, right? You go out there on, one sunny day in maybe June or something, everything looks good. Groundwater's not too close to the surface, get the permit. But as we know, these systems can be in the ground for decades and conditions can really change. Local governments are the other entity that, that could be involved here. And local governments are at the front lines of most adaptation planning. They have critical land use planning and zoning authorities, but unfortunately their authority to directly regulate on-site systems is very much unclear. Except for we just did an analysis here at UGA on 4 southeastern states, South Carolina, North Carolina, Florida, and Georgia. And Florida is the only state that has specifically given local governments the authority regulate on-site wastewater systems in all the ways that they might choose to. In the other states, it's possible that they have the authority, but it's also possible that state law on the issue preempts them from adopting some local rules. And no courts have yet decided any cases concerning this in any of these states. So the question is kind of up in the air. As Jane and Mike both said, we're looking at 2 states as part of our analysis, South Carolina and North Carolina. So I'll just give you a little bit of detail about those states' regulatory regime as to this question. When we're looking at whether or not a local government might be preempted by the state, the comprehensiveness of the statutory program for regulating these systems will be taken into consideration. South Carolina's is rather haphazard. They deal with on-site systems in a bunch of different places throughout their statutes. So that's a tick in favor of maybe local governments not being preempted. South Carolina is very interesting that the intent or the purpose of their on-site law is to abate obnoxious and offensive odors, which I forget what year that was written, but it was quite some time ago. So apparently if your septic tank doesn't stink, you might be okay. The rules have not been developed just to address odors, but I thought that was pretty interesting. Permits may be revoked for major system malfunctions, but they only have 6 inches of separation from groundwater for many systems. That's that vertical separation distance. And as Mike indicated, at least 3 feet is what you're going to need. So 6 inches is really not what we want to see there. North Carolina, where most people on this call, I assume, are from, has a much more comprehensive septic statute. It's all laid out in the statute. It's pretty thorough. The focus is on public health, like most states, not as much as on environmental health. Permits can be valid without expiration, however. There's an interesting thing in North Carolina state law that allows installation permits to be valid forever. And local health agencies may petition for stricter standards, which I think is another tick in the other column in favor of the state possibly preempting local government action in these areas. North Carolina has a comprehensive statute, and they've already created a place where you could have stricter standards directly regulating these systems. So I've talked way too long already. There's a lot of fun stuff about legal authority, but I'll pass it on back to Jane to finish this up.
All right, I think I'm just going to say we've got a lot more to do. We're going to do some economic analysis, water quality work, and I'm going to turn it back to our host, Rebecca. And acknowledgements are here as well. We've got a lot of partners on this. Thank you.
Thank you all for those really fantastic presentations. I learned so much about what's happening on our coast, how our groundwater levels are changing, and how this relates to wastewater treatment. So we are kind of running up against the end of our webinar time. So what I'm going to do is just really quickly share my screen again, and hopefully everybody can see this, I hope. If any attendees have questions, please do type them in the chat. I've collected them along with Tom Maycock, and we're typing up notes. I'll send these to the speakers in case they can respond. I saw that Rick just entered a response in the chat. I do apologize for not keeping better track of time during this. I was really enthralled with all the presentations, so that's on me. I guess in our 1 minute left, though, if any speakers want to reply, this is kind of a question that we've asked everyone is, where do you see the research going over the next 5 to 10 years, thinking about climate change and sea level rise and its varied impacts on the coast of North Carolina? What are those big research questions that we'll be addressing?
Well, I mean, I'll start, I guess, and I alluded to several of these during the presentation. I think we continue to try to predict what the future is likely to look like, and in terms of the natural systems that the Earth comprise the Earth, and so we will continue to try to get a better handle on one of the biggest, again, the biggest impact factor for us is global mean sea level. One of the biggest unknowns is the contribution to global mean sea level from glaciers, particularly in Antarctica. And so that is a huge area of research, but just generally continuing to put the pieces together so that we have a clearer and clearer picture of what we're likely to be confronted with over the course of the next 8 decades as we get to 2100 and then beyond. We started looking at things beyond. And so trying to put that together with more certainty and clarity is definitely area of active and research, and will be for years to come.
Yeah, I'll just chime in too. The other aspect that I think is really important is for some of the adaptation plans, how are we going to pay for it? So the economic side is that ties in a political well too. But as Rick said, some of the uncertainties, like we're pretty certain about some aspects, and then if things change quicker than we expect, that the timeline for action too is real important.
I would second what Mike said emphatically about figuring out how to pay for all of this. And also I think identify a lot, and some of that actually works in well with the identification of all of these different regulatory barriers that exist. Because wherever you look, you start looking into it, you realize they're very prevalent, and we might know what we want to do, but we've got to figure out whether or not we can under our current regulatory and policy regime, and what needs to change in order to get there.
And one other thing I'll just mention is I see this research with the wastewater operators and the health regulators. What it does is it helps us to to establish relationships with the folks ultimately that can advocate for some of these changes, and we've got to be interacting with these kinds of folks who are really doing this day in and day out, because I think if we come from just kind of like a climate change research background or whatnot, that's one kind of small constituency, whereas if the wastewater operators can say, I see with my own eyes, we have problems on the ground right now, not just in the future, that is going to have, I think, a bigger impact in making some policy changes.
Thank you for those really well thought out responses, and I look forward to seeing where the research goes, and maybe my office or NKICS or anyone else on the call, if we can be a part of it. With that, we'll end the webinar officially. I will stay on if anyone has any questions that they want to send me. I'm going to throw a link in the chat real quick. If you have not yet registered for the final webinar in the series, please feel free to register now. There's that Google form link. Speakers, you're also welcome to register for this too. It'll be on talking about climate change. It's scheduled for December 15th, same time, 10 to 11:30 a.m. And yeah, I just really appreciate all of our speakers today giving us your time and your expertise. I really appreciate it, and I'm really excited to know more about what's happening in our state. So thank you.
Thank you.
Thank
Thanks,
you.
everyone.
Have a good weekend.